Should we talk about things that we don't really know or understand? Hello, everyone. My name is Jeremy, and today we're going to do just that. We're going to talk about neural nets and a little bit about machine learning. Something that I don't really understand. But using the model Talk It Out, we're going to learn that there is a great value in actually trying to explain something that you don't really understand. Because in the process, we correct ourselves by connecting something that we do understand to something that we don't fully understand. And a lot of times, we can use analogies and figurative speaking. Understanding again that using analogies and figurative speaking often leads to kind of errors, inaccuracies, and overgeneralizations. But just like a neural net, this is great. And we're going to talk about why that is today. So, the reason why we're doing this is because I have a student who is nudged by his parent to talk about AI and machine learning. And unfortunately, this tween doesn't know advanced mathematics. I believe neural nets use multivariate calculus, linear algebra, among other things. Again, the type of mathematics that you learn in the tail end of high school and then in university. But he doesn't have this. And he has the task of explaining neural nets to his peers. So it came to me. And today I'd like to share with you one way that we might be able to do just that. So let's get to it and think about neural nets using analogies. So the most natural analogy that we make between neural nets and other things are, of course, a mind or a human mind. And like the human mind, we think of the human mind as a mapping. On one side, we have the input side. On the other side, we have the output side. And going through some sort of maze of connections, we somehow connect these pathways between different inputs to a particular output. So we think that's how our minds work, and we think that's how neural nets work. Well, we know that's how neural nets work. And like a mind, um, it makes guesses. Initially, things go forward and we try to make this connection, but sometimes we make the wrong guess. And then we get feedback, and then we make corrections. And then the second time we guess, we're more and more correct. So that's another thing that our minds and neural nets have in common. So how does this done? Well, we believe that our minds are moldable, that we can shape and restructure these pathways so that the proper connections, the proper associations are made over more and more and more iterations. After an average of different exposures to different things, eventually these pathways are connected more and more properly, just like our talk here, maybe a bit inaccurate. Eventually, we have a more and more correct mapping or correct connection. So that is a great way of thinking about the connection between our minds and neural nets. So another thing that we can think about that might be useful is if we were cavemen, if we didn't have powerful computers that could simulate these networks, these pathways, how could we do it? So we know the mind is moldable. Uh, so let's think about a material to make a Stone Age caveman neural net. Let's use something like some putty-like clay that you could stretch and impress and bend and reshape. And we don't have electricity to or software values at or transistors to hold charge or to do this electronically. So instead of using charge values, let's use marbles or round stones. And so we know that a neural net and is that just that, a network, and it consists of different points, different pockets, or, right, different charges, so different points. Just like our mind is like a nerve cell, which has like a head and a tail. Maybe the head holds some charge, and then it has a tail, and it connects to another nerve cell, and then so forth. And what happens then is we think that in our mind, to form this mapping, how does it work? Well, there's this, on one side, an input layer of nodes. On the outside, we have these output layer of nodes. And how we might think about it is that when certain input nodes fire together, they connect and then they charge different patterns of nodes in the next layer, and then in turn charge different nodes or different cells, different nerves on another layer, and then another one on another layer, and so forth until we reach the output node. And that's how this pathway along this large network maps or connects an input to an output. And so we want to do the same thing with this moldable clay neural net. So how could we do this? Well, in a clay example, we can do things like stretch the pathways between the different pockets, right? We could change the angle of things or put reservoirs to trap extra stuff, or we could maybe put a pocket to deflect certain things. So the idea again is that how would we get this neural net to work? We would take the input and we have output layer. The output layer is we could have like maybe jars on each output node. And on the input node, we would spill marbles. And if this was an uneducated neural net, the marbles poured in different input nodes would roll down through this clay maze, and they would spill into different cups at the end. And the cup with the most number of marbles would be our answer. So for example, maybe we could take a picture of a chicken, right? And we could divide the chicken into 100 different squares. And we could have 100 input nodes. And we could look at the first square and say, does the first square colored dark black? If so, let's put 10 marbles and dump it into the first square input node. And then we look at the second, excuse me, square in the picture. And if it's a light gray, maybe we put 5 marbles and dump it down in the second input node. Then we look at the next square and the next square. Oh, the 55th square, it only has an empty space. So we put 0 marbles down the 55th input node. And then we look at the 100th one and so forth. So we're pouring all these marbles down into this clay maze. And if it's totally unconfigured, in a random fashion, marbles will bounce down, 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 down across the different layers. And they would spill into these jars at the output nodes. And each jar would be maybe labeled with a different animal, right? So maybe it would say, there are 10 marbles in the donkey jar and 5 in the ox jar and 55 in the goat jar. And then if that's the case, we're going to misidentify this picture of a chicken as to that of one of a goat. And that's obviously not what we want. So it's an uneducated system. So what can we do about it? Well, excuse me. One thing that we can think about is that if we can press and shape this neural net by maybe widening certain pathways or adding certain angles or curves or pockets in the different nodes, we can influence how the marbles roll down to the jars, right? And that's exactly what we want to do with a neural net. A neural net works on the concept that we have something called activation, that certain nodes, certain points fire strongly, which in turn influence how the next layer of nodes fire, which influence how the next layer of nodes fire, which influence the next nodes, all the way down to the output node. And if you think about this marble, this Stone Age example, the number of marbles passing through a particular node is the activation, right, of how much energy is going into each of these nodes. And then, which eventually connect to the last jar, which is the jar with the most energy, is the answer of our guess. And so that's the first kind of analogy that we can make between a real neural net and this theoretical Stone Age man's or woman's neural net. And like a real neural net, the Stone Age neural net has the concept of the idea of being able to mold or reshape the neural net. So in a real neural net, we have this idea of weight. We can amplify or multiply or strengthen the connection between different nodes or different nerves of each layer. And just like a real neural net, we can give a bias saying that these two nodes probably should be very strongly connected, and these two should not be very strongly connected. And we could do this with our clay or our moldable neural net by adjusting maybe a certain deflection angle or adding extra pockets and repositories of more or less marbles to strengthen or give a bias to whether or not this the marbles pass from one node to another. And now we have a way of molding and configuring and tuning and educating the pathways along this neural net. So, I mean, if we were to design this and think about this humanly, what's happening is each input node or each input position is accepting marbles or accepting charge or accepting energy. And those are associated with a particular point in space or a particular criteria of our input or information. And as we go along the different layers, each layer can work on successive patterns. I mean, for example, if we're looking at a picture of a chicken, maybe we're starting to look at lines and curves in the first layer, and then maybe we're combining lines and curves to make a shape of a beak in the next layer, and so forth, the feathers in the next, and is there a body in there? And then combining these things, does it have a beak and a body and two legs? And as we send more and more pictures, different groups of nodes will fire together to associate or to be connected to a particular pattern. And as we approach the second to last layer, if we were to do this in a very intuitive way that the humans would do it, we would probably start grouping together all of the criteria. Does it have this, 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 and this? If so, it's a chicken. If it has this, this, and this, and this, right? These clumps together, then it's a cow, and so forth. Realistically, I'm sure that computers work very differently than that. They probably don't consider the same patterns that we do. Probably what they perceive or what they're keying on is probably very different than what we would key on. But this idea that each successive layer is accumulating patterns and associations. And so when certain clumps fire together, they're most likely going to connect to a particular output. And that's the idea of a neural net going forward. And so the forward phase is like the guessing phase that even we do. And we make all kinds of mistakes. And then we get the output. So again, maybe this newborn baby clay neural network gets all of these marbles. And if it was done properly, maybe 1,000 marbles would end up in the chicken jar. And we're confident that we saw a chicken. And then we pour one of a cow, and then we have like 900 in the cow jar, and maybe 10 other places, and we're pretty confident that that's a cow, right? But it's not going to happen like that unless we tune and shape this um, this clay structure. And of course, what's going to happen as we impress it and press it properly, um, an average of the appropriate pathway size or weight will be done. And as we adjust certain angles, certain biases will be formed to prefer certain connections. And if we average it and average and average it, um, hopefully we won't just use the last impression, but there would be an optimal compromise between the different pathways and different pathways such that we have one that works. That when we pour the marbles on the input layer, eventually the majority of the marbles will land in the right output jar. So that's, in a nutshell, how we would like our neural net to work going forward. We have this idea of the input layer, which we put energy down, and then we have the output layer. And the most energy that collects in the output layer is our guess. And then we have the hidden layers in between, which are highly configurable, highly adjustable, highly tunable. And we call those parameters. We have something called weight, which is how many, in our case, how many marbles can pass through a particular vein or pathway to the next layer. And if you think about that, that could be like the width of our clay structure. We can make certain pathways wider by stretching them out, or we could shrink some of them by squeezing them together. Of course, more marbles will tend to flow through the wider pathways. And we can add biases by adding certain angles or cups or repositories that might spill extra marbles, right? Which might mean if only one marble goes into this particular node, it might be enough to spill 20 marbles into the next two nodes neighboring it in the next layer. We're configuring and shaping the connections, the associations between certain patterns that should be recognized so that we come to the right output. But how do we do that? And that's really the magic of neural nets. It's this idea of back propagation, which is a fancy way of saying, after we made our guess, let's find out whether we did it well or not. And if not, or even if we did well, whatever the case might be, we're going to shape the neural net from the output side to the second last one, to the middle one, to the to more forward, all the way back, and reconnect the pathways very strongly back to the input. So, for example, let's say we have this picture of a chicken, and as we did before, for every pixel or every square in a chicken picture, we pour the right number of marbles, and we end up with excuse me, only a few, or even doesn't matter. we have our associated marbles in our jars. And what we want to do is then have a count of the activation in each node in our network. So for example, in the second last layer, maybe we have a turnstile counter, which counts the number of marbles that pass through that node. Those are obviously firing with a lot of activation. They have a lot of energy going through there. And what we know that we want to do is we want to connect these high firing nodes to the chicken node. So if you look at the second last layer, maybe there were not a lot of marbles flowing to the chicken jar from that second last layer. So what we need to do is we need to change it. We have to change the bias, and we have to change the weight. We have to widen those pathways. So now that what was previously weak is now strong. We know that this node fired, so that should go to the chicken jar. And so we do that one layer at a time. And then we go back and we say, well, from the second last layer to the third last layer, there was these really strong activations up here. And we've made a strong a strong road from the strong pathway from the chicken jar to the second last row. Now we need another strong strong pathway or bias to the strong activations in the third last row. So we do our adjustments in clay, and then we go back to the fourth last row and the fifth last row and the middle row and then the forward rows until we have this really strong network of pathways flowing from the inputs to that chicken jar. And then we take another picture of a different chicken at a different angle, and we do the same thing. And then we get a picture of a cat, and we do the same thing. And we do the same thing with a dog, and all the different animals. And we try to mold it. And hopefully, if our clay is not like just just gets fixed into the last the last impression, but maybe has some memory so that it stretches and kind of bounces back. There'll be an average after stamping that clay so many times. It will get an average of all of our pushes and pulls, and now when we pour our marbles, we get the best guesses usually. So that's the idea of back propagation. How do we re-educate the this neural net to perform properly? And I had something that I want to talk about. The other thing that we can talk about is the idea that this is not perfect, right? Taking this approach will not lead to the most fastest path from one side to the other, and it may not even lead to the right path sometimes. Taking this approach, because we're only going based on strong associations. We're not making a direct line by directly adjusting the path, right? We're just putting strong associations. So sometimes this neural net will make mistakes, right? Potentially, because we may make the right path and then we make an adjustment. So this is the idea that even if we have a neural net, it's not always going to be having the right information. Sometimes it's going to get to the wrong pathways and it may make a wrong guess. And we expect it to, but hopefully after we correct it more and more and more, after a million times, a million times, it will get better and better and better and better and better and better and better as it gets more and more tuned. And that, in a nutshell, is how we can think about neural nets in a very basic way, almost like even a child can understand. We have this idea of input nodes, with the idea of output nodes. Input nodes is where we group and send information into different input funnels, and the output node is the ending guess. And we know that we have a hidden layer where we have a big maze of nets, of roadways, networks, and paths, and we can adjust these things. We have these ideas of weights that, excuse me, could be like the width that predispose how information flows from one layer to the next. And we have this idea of biases, which can determine how much one layer affects the next. So one node in one layer affects the next node in the next layer. And we have this idea of kind of grouping up patterns of nodes to come to our output. We also have this idea of back propagation, that we use the information. We have this thing called a cost function. We see how much difference there is between what we want to have, aka 100 or maybe 500 marbles or 1,000 marbles in the marble jar versus all the number of marbles in other jars. And that gives feedback information, whether or not this is good or not. And we use that to reshape our pathways. So, for example, if we want something to be, if we want the activation to be closer to what we want, we can use that. Actually, we'll talk about that in a future lesson. We'll talk maybe about this idea of gradient descent. But let's do that another one. So, but the most important idea is that we can go backwards one layer at a time and try to adjust our neural net by remolding it with these ideas of weights and biases, such that the next time the neural net will be more accurate, and then we do the same thing again, And then we do it again and again and again, constantly giving it feedback and reshaping the neural net. And as we have an average of all the reshapings, it will perform better and better and better, understanding that sometimes there's still going to be mistakes and sometimes it's going to be inaccurate. So there we go. There we have it. The idea of a neural net symbolically as a analogy rather than going through any kind of mathematics. Hopefully this has been valuable to you. And again, I admit that this may not be a very accurate reflection of exactly how neural nets work, but it gives us a starting point. Just like a neural net, we're pushing forward some ideas. And so I invite anyone with a better idea or a better way of explaining it that would be useful for someone without any kind of mathematical background to push back and go do some back propagation to help make this a better and better analogy over time. So there we have it, a neural net for a fourth grader. Thank you very much for listening, and I hope you enjoyed this.